This morning you saw how outer approximation works, which is one algorithm for solving mixed integer nonlinear optimization problems. Then we introduced this branch and cut framework, which is a very sort of generic framework. And now I'm going to tell you about the first algorithm that was actually developed for solving nonlinear mixed integer optimization problems. So NLO, nonlinear optimization-based branch and bound. And the interesting thing is that when this algorithm was proposed in the sort of early 50s, 1950s, there were no solvers for nonlinear optimization problems really, or no good solvers for nonlinear optimization problems. It was mainly linear programming, and so it was proposed and implemented mainly for linear programming. But the concepts, the authors realized this can be used for nonlinear optimization as well. So this very general, generic concept, and a very easy algorithm to implement, but not necessarily efficiently. Implemented efficiently, that's harder. So again, we're looking at our mixed integer nonlinear optimization problem, minimizing an objective function and constraints. And now I'm back with the formulation where we minimize the objective. So we don't, for this algorithm, we don't actually need the trick that we put the objective as a constraint. And the assumptions that we make here is that the feasible set, so the set of all points that satisfy the nonlinear constraints and integrality are somehow contained in a bounded polyhedral set. Maybe somebody gives us lower and upper bounds, for example, on the variables. And the functions are twice continuously differentiable and convex. Convexity is important to guarantee that we find the global solution and don't give you the wrong answer. If the continuous differentiability or twice continuous differentiability, that's really convenience on my part. You can still define this algorithm if it's only continuously differentiable, and even for non-smooth functions, you can define the algorithm, but you may need a different solver that can handle non-smooth constraints, non-smooth objectives, harder for constraints. So the most restrictive assumption is the convexity assumption, because it restricts us to a certain class of nonlinear problems. And the third assumption is just something that is a technical assumption. You can probably get away with having a weaker assumption there if you ensure that your solver somehow manages to terminate in a graceful way if these assumptions are violated. But that's an implementation issue. So then, together with the mixed integer nonlinear optimization problem, we also have this relaxation, where we now relax integrality. We ignore the fact for the moment that our variables y are integer and just set them to be continuous. And so this is now a nonlinear optimization problem, and there are lots of good solvers, open source solvers that solve this problem. And the cool thing is, if you solve this problem and all your variables happen, the integer variables happen to be integral, then you know that you get the global solution to this problem. The reason for that is that because it's a convex problem, the nonlinear optimization solvers are guaranteed to find a stationary point. The stationary point is a local minimum. Every local minimum is a global minimum. And this global minimum is also integral. So that's the best you can do. And likewise, if the relaxation itself is infeasible, so if there's no continuous points such that the constraints are satisfied, and we had an example earlier when I introduced the infeasibility lemma, then the mixed integer nonlinear problem is also infeasible. So those are the two cases in which case we can stop after just solving the continuous relaxation. That normally doesn't happen, and so instead what we then do is we create a tree that's going to search subproblems where we've appended bounds on the integer variables to the original nonlinear constraint optimization problems. And these bounds reflect the fact that we're branching, and they allow us to create a branch and bound tree. And notice that the original the nonlinear optimization relaxation is just equivalent to setting these bounds to -infinity and +infinity. So that means you can ignore these bounds effectively. Okay. So then here's a one page that describes how branch and bound works. So we solve a relaxation, and so for example, in the special case, when the integer variables are binary variables, we just relax them to be continuous, and then we generate this binary tree. So at the very top is the root node. So this is a tree that's upside down, but it's easier to depict in this way. And then we pick a variable that's non-integral, and we branch on this variable by setting it, in this case, either to 0 or to 1. If we continue doing that, then we create this search tree. So once one of the variables is fixed to 0 or 1, some of the other variables might be non-integer, and we fix them to 0 or 1. When we're searching this tree, it could be that at some node, the problem becomes infeasible. So there's no point that satisfies both the bounds that we have added and the nonlinear constraints. And if this node is infeasible, then we also know that adding more constraints will not create a feasible problem. So we know there are no feasible points or no feasible solutions below this node here. And so we can effectively stop searching the tree at this point. So this is where we don't have to go any further. Occasionally, we find a point where we get an integer feasible solution. So if we branch long enough, and this morning we had the exercise, if we have p binary variables, then the depth of the tree is at most p. So if you go down the tree after p steps, you will be at an integer point. And if this point is also nonlinear feasible, then this will provide an upper bound. Do you know why it's an upper bound and not the global solution? Anybody? Yeah, there could be somewhere else in this tree, this is a big tree, there could be another solution that's better. Yeah. So, but it gives us an upper bound, and we're going to use this upper bound to try to prune or remove other nodes from the tree. So for example, if we find a node where the lower bound at this node is now above the upper bound, then we know that this node is no better than the one that we found here. And in fact, even if we branched further by introducing additional constraints, we drive this upper bound, lower bound further up, so we know there's no better solution. So like with the infeasible one, we can also stop branching here, and we can also stop branching there. And we do this until there's no unexplored nodes in the tree. And there's a whole bunch of solvers. This is an old list. So Zahanides has a global solver called Baron. Pietro has one called Quen that also, in addition, branches on non-convexities. There's some branch and bound solvers. GAMS has one, a very old one, and I have a very old one. There's also newer solvers that are also hybrid solvers that I'm not listing here. So for example, Bonmin or Minotaur are much more powerful solvers. So here's the same picture in a formal algorithm. If you want to implement this, we use a heap to store the nodes of the tree or the changes to the bounds. And initially we put the relaxation, the root node relaxation onto this heap. And then we go through this little loop where we take any problem from the heap, and choosing a problem is actually not an easy decision. So which problem should you solve next? If I go back, even after a few branches, you have a lot of options of which problem to solve next. There's some advantage on just going down the tree, on diving, because that means the changes to the previous node is small or limited. But sometimes it's also good to look for nodes which have good bounds, because you want to find good solutions. So there's different strategies there. But let's assume all you need to do is really find one of the problems and take it out. Solve that problem. So you need to solve a nonlinear optimization problem there in the red line. And that's quite expensive. And then given that solution, you then have a number of options on what you need to do. If this problem is infeasible, then we can just prune the node due to infeasibility. So that was the red node on the previous slide. If the solution is dominated by the upper bound, you can prune the node. So that corresponds to the blue dot here. Oops, wrong way. And if it happens to be integral, so you have an integer solution, then you know that you have a new upper bound, right? Because it didn't satisfy this, so it's less than or equal to u. So at worst, it's just the same solution. Okay, and so you update your incumbent, your current best solution, and if that doesn't work, then you need to branch on any of the variables. You pick a branching variable, and choosing which branching variable to branch on is again a decision that's quite important in terms of the effectiveness of this algorithm. And so there's a number of choices here. One is which problem to solve next. You have this big tree, thousands, tens of thousands of problems, and maybe how to solve the problem is another option. So you have different optimization solvers, and then which variable do you branch on? So those are implementation questions. But any way in which you implement this would be an algorithm that would be convergent. And the convergence proof is the same as for mixed integer linear optimization. So it's easy to see that this branching that you do, the branch and bound tree is finite as long as the feasible set is finite. So there's only a finite number of integer points that you can get to, and eventually the worst thing you can do is enumerate them all. So that's very bad. It's exponential complexity, but you know it is finite. So that's nice. And then the theorem says that if the standard assumptions hold, then the branch and bound terminates at an optimal solution or with an indication that the problem is infeasible after a finite number of nodes. And the proof is really not hard. It's the same as for mixed integer linear optimization. Under the technical assumptions, I know that I can solve every nonlinear optimization problem to global optimality because I have a convexity, a constraint qualification, and the problem is smooth. So those are the assumptions that guarantee that our solvers find a global solution. And then the boundedness of the feasible set ensures that this tree cannot grow to infinity. And so you get convergence. And there's a theorem in this nice book by Lex Schreiber, if you want to look it up, theorem 24.1, that basically is the same theorem that shows that this is a convergent algorithm. So you can go away and implement this, and in principle you can even implement this in AMPL if you wanted to. You need to find a way of somehow storing these bounds, but you can do that. That's possible. So we had this picture earlier, and Ashutosh is actually the one who generated this picture on one of our examples. There are some tools which allow you to actually print branch and bound trees. So this is a branch and bound tree that we generated with Minotaur for a synthesis problem after 360 seconds. So these trees get really very big. So a couple of things: you need to be smart about solving the nonlinear optimization problems, but more importantly, you need to be smart about searching the tree. Okay, so let's just stop here for a moment and see if there's any questions about this very basic algorithm. So this is not something you want to maybe implement, but variants of this you would maybe implement. Everybody's okay when I say this is a finite, globally convergent algorithm? Yeah?
From application point of view, is it very different from the nonlinear that we apply branch and bound in these problems?
Yes. So the question is it very different to the linear case versus the nonlinear case? And yes, it is very different. And the main difference is that as you're going through the tree, in the linear case, these moves that you make, the linear problems that you solve here are very close to one another. and you can reuse basis information or factors of the basis matrix. So if you know about the simplex or dual simplex method, they store factors of the basis matrix, and you can reuse these factors. In nonlinear programming, you can never do that, even if you had access to these factors, because a nonlinear programming algorithm works iteratively, and so it sets up factors at a point xk to produce a point xk plus 1, and if that is determined to be the solution, it never refactors at that point. So the factorization is always out of date. They're always one iterate out of date that you would get out. And so we have, Ashutosh and I had worked on an algorithm, but we tried to do something about this by reusing as much information as we could, and that sometimes helps. So in the nonlinear case, you're almost always restarting the nonlinear optimization, and you cannot take advantage of the factorization. And the factorization is the most expensive part in the simplex method, and also for nonlinear optimization. So so that's the main practical difference between those two techniques.
And also the selection of variable inputs, like here it is a binary, so we can have the two inputs value for the x and x.
Yeah.
0 and 1.
Yeah.
But if we have multiple integer values.
Yeah.
So branching on which variables input, like 1, 2, 3, 4.
Yeah.
Is it different from the normal, or is it the same?
No, it is the same. So the branching strategies, the node selection strategies, they're very much the same. And I'll show those in a moment. So again, there's no difference there. The main difference has to do with the fact that the solvers don't allow you cannot reuse the factorization. So you're stuck of having to refactorize. And for the simplex method, a factorization is an order n cubed operation, whereas a solve is an order n squared operation for dense systems. For sparse systems, it's slightly different, but you still have an additional overhead that you never have for the linear problems. I might show some results of that tomorrow, maybe. So this basic framework will work. There's a proof that says this will work, but it'll work in a terrible way. So there's a number of things that you need to do. You need to select good branching strategies, have a good node selection strategy, maybe think about inexact nonlinear optimization solves, cutting planes, and then software design, and just how to store nodes on a tree and access them efficiently. So a lot goes into developing these solvers that wasn't in there. So ideally, what we want to do is choose the branching variable or sequence that minimizes the size of the tree. So if by some magic, there is a tree that's the smallest possible tree that you need in order to prove global optimality. I think that's a theorem. You can try proving it. I'm not sure how I would prove it, but there is a tree that's the smallest possible tree. But we don't know what that tree is. One way of doing this is then to choose the variable that maximizes the increase in the lower bound. And so you start off with a set of candidate variables in some set IC, that's the subset of the integer variables that you have. And so you might choose, for example, priorities. A very important aspect is that users often have a good idea of branching priorities, and they can tell you about this. So switching a piece of machinery on and off, a distillation column on and off, is more important than choosing the number of trays in the distillation column, because if you switch the distillation column off, then there are no trays, and the whole set of binary variables will be set to 0. And so if you know which variables are important, and the users can tell you that, then that's usually a good thing. So one way, a very bad way, is branching on the variable with the largest integer violation. And Tobias Achterberg did some experiments with this, and actually observed that doing this computation is almost as bad as random branching. So randomly selecting a branching variable means you don't know nothing about your problem, or you pretend you know nothing about your problem, and you choose something at random. That can't be a good strategy. There must be a smarter strategy. And so this is a bad strategy. So this just looks at the, it maximizes the smallest deviation to an integer. So, okay, so this rule, another way of looking at this rule picks the variable that's closest to the halfway point between two integers. So, and that seems like a sensible thing to do, right? You want variables that are, things that are near 1 or near 0, you might not want to branch on. This seems like a sensible thing to do, but it's really a terrible idea. So, instead, good rules estimate the change of the lower bound that you get out of making this branching decision. And so this requires a little bit more work or computational effort in order to get this information. So what you can do is you can actually look at getting degradation estimates. So when you are making a branching decision, what you have an objective value here, which I call f hat, and then after you branched, you would have a new value here, which if you branched on fyi less than or equal to the floor of yi, and here yi greater or equal to the ceiling of yi hat. So over here you get an fi branching down, and here you get an fi for branching up. And ideally what you want to estimate is how much do you change this bound? And so you can combine these estimates, and you can look at sort of the estimate. You want both of them, so you want the degradation in both directions. So both of these will increase the objective function value, and you want to somehow make those both close to 1. So you want to choose the variable with the best degradation effort. And there are different ways of computing these degradations. So in this case here, one way of computing this degradation is actually to just solve these two problems. And then repeat doing that for all I. So you do this for every integer variable that's at a fractional value. So that seems like a lot of effort, but that is one possible way of computing these degradations, which then is di minus is fi minus minus f hat, and di plus is fi plus minus f hat. And both of those will be non-negative because you added a constraint in both cases which pushes up the objective function. So here's a couple of ways of how you can compute those. So the first one that I indicated over there is called strong branching. So did you have a question? No, you're just stretching? Okay, good. If you're stretching, that's good. So strong branching basically says what I told you over here, which is solve these two problems. In fact, there are 2 times the number of fractional integer variables problems that you need to solve to get these estimates. And then compute these degradations. So FP here is the parent one. So this would be this one here. That's the FP. So now the notation matches. And there is some additional advantages in this because, so first of all, if it turns out that both these problems are infeasible, what does that tell you? It probably tells you up here. You can actually, if both these problems are infeasible, then you know that this node is also infeasible. Because eventually you will have to set those guys to one or the other. And this is a variable, this is a valid branching, so you know the root, the parent node is infeasible. If one of them is infeasible, so if this guy is infeasible, then you can actually fix, you can fix the variable or you can fix the bound to the bound on the right for the remainder of the tree. And for every problem, that's a child of this parent node. And there's alternatives to this that are based on approximately solving these nonlinear optimization problems or estimating the cost of branching in these two directions as you search the branch and bound tree. Yeah.
One is invisible, then it's completely infinite. The second one.
The second one, this one?
Yeah, this one. Yeah, I get understand.
Okay, let's do that real quick. Okay, so let's assume that this guy is infeasible. Then that tells us that for any solution here that's feasible, the only way you can be feasible, you cannot be feasible if yi is less than or equal to the floor of this. So this direction now is infeasible. And so by fixing, it's not the right word, by fixing what I meant to say and what I should have said is you can now add this constraint to the parent node. Because you know that if you tried to do this part, it would always be infeasible. Does that make sense? I can try again. So there are no feasible points here if yi is less than or equal to yi hat, the floor here. If there were binary variables, then you could fix the binary variable here. So this would be 0 and this would be 1, then you would fix it to 1. Because once you put 0 in, you know you didn't get a feasible point here. And that's irrespective of whatever else happens below. So you know if this is infeasible, there's nothing below this that would be feasible because you're adding more constraints. Okay, so we tried something where we looked at simple approximations. Instead of solving nonlinear optimization problems at these two nodes, we took the last solution of the nonlinear optimization problem here, the last quadratic programming approximation, and we used that to estimate these costs. And you can do that, and you can do this in different ways. You can do a full nonlinear optimization, and so here's a number of problems that are not too large. And if you do a full round of strong branching, it takes sort of this many seconds. If you use just the QP solve instead of the nonlinear optimization, you just say, I'm just doing one quadratic programming solve, it's still prohibitive. But if you use the hot start capabilities, and that's similar to the dual simplex method that's available for linear programming, then this becomes much cheaper. So this is really nice. You can now do this at a fraction of the cost of doing that, and you get reasonably good bounds. So you sort of get an order of magnitude by reusing the factorizations of the equivalent of the basis matrix for quadratic optimization problems. And the factors there are much more expensive, which is why this difference here is so large. So in linear optimization, this difference probably isn't as large as here, but because these factors, the initial factorization is more expensive, this is much more significant. So if you branch on special ordered sets, I think we looked at this very early on when we introduced special ordered sets. We had a picture on how to branch on these, and the way to do this is actually to compute the center. So your fractional variables, if the yi hat are fractional, then you can still compute the center value of your diameters, for example. So think of the di's as being the diameters in your water network that you're selecting, and you're then finding the index I0 that encloses d hat. And then you create two nodes where you either set the first everything to left of d hat equal to 0. So this node corresponds to saying d hat has to be greater or equal to di naught plus 1. And this corresponds to the node where I say d hat has to be less than or equal to di 0. Okay. And so you're branching, so that's one way of branching, and it's a very efficient way of branching because this is much more efficient to branch on the special ordered set than on individual binary variables. So you should never branch on binary variables that correspond to a special ordered set. That's not very efficient. This is much, much more efficient. And it also uses the problem information, right? It uses the fact that what you really want to branch on is this d hat. You only introduce the binary variables for convenience because you didn't want to implement a special branching rule for branching on these discrete values. So that's why this is a much better way of doing it. But you can branch on other things. So you can branch on split disjunctions. So what are those? Let me see if I can draw a picture and get it right. I can create my integer lattice here. And I can now take, I have to take a direction, an integer direction, so I can take, for example, this direction here. And then if I'm careful, I need to be careful if I do this right, I can branch by saying I'm either in this direction or in this direction. So I can go to, that's actually not the right, I don't think that's the right, that's one way of doing it. I probably want to do it so they're integers, yeah. So I can also branch in sort of other directions than just the coordinate directions. So the normal branching works by branching on sort of coordinate directions, but I can alternatively, I can rotate my coordinate system and branch on other coordinate directions, as long as I make sure that I'm not eliminating points that are suddenly caught in between. So I have to be careful about that. And that's why I was drawing this picture with a bit care. Okay, and then the last part is node selection. I'll do this try to do this really quick. So initially you want to find a good feasible solution quickly, and a good way of doing that is actually to do depth first. So just go down the tree and find a good integer solution. Later on, you might want to want to prove optimality of the current solution by increasing the lower bound, and so then you would skip to something like a best bound search. So you choose the node on or the problem on your heap that has the best bound so that you can eliminate it quickly. So depth first search is very easy. You always select the deepest node in the tree. It's easy to implement. I like that, and that's the first one I ever implemented. It also has the advantage that it keeps the heap as small as possible. So if storage is an issue, you can do that. And it minimizes the change to the next nonlinear optimization problem, because all you're changing is one bound. If you bounce around the tree from side to side, then many more things changes, and so this is better for hot starts. But it doesn't work very well if you just rely on this. So you have to switch to other things, and best bound is a good strategy where you select the node with the best lower bound or the best expected value sometimes. And this minimizes the number of nodes for fixed sequences of branching decisions. But it requires more memory, and it doesn't have the same opportunity for warm starts here. And it sometimes only finds integer solutions at the end. So if you're interested in finding integer solutions quickly, then you want to have a strategy that goes down the tree as quick as possible. There are many other strategies, by the way, for specific problems. So for a gas network design problem, we found that it was good to sometimes go down the tree a little bit, but then don't backtrack too far. So we had a sort of threshold of how far we wanted to backtrack, because solutions lower down in the tree corresponded to decisions that were made later on a time horizon. And so we wanted to have make good decisions early. Here's a little trick that Ashutosh implemented when he was working with me at Argonne, which was that we don't like solving nonlinear optimization problems, so why not just do QP solves? So for the moment, we can just ignore the fact that we have to solve nonlinear problems and just solve a quadratic programming approximation. So this is great because it means we can reuse the same factorization, and this is almost as fast as using the simplex method or dual simplex method now for searching the tree. There's a couple of caveats. So one is that if you find an infeasible node, then are you still allowed to fathom that node or not? Quick poll. Who believes we are allowed to fathom this node when we're only solving quadratic programming or quadratic optimization problems? Are we allowed to fathom? Okay, 1, 2, 3, okay. Or we are not allowed to fathom. Okay, I fooled both. So yes, we are allowed to fathom. Why are we allowed to fathom? It is a relaxation because we have a convex set. We have one outer approximation, so that's a relaxation. So infeasibility is okay to fathom. And we can use a similar trick for the linear part of the objective function. And so we rewrite the objective function in a slightly different way, and then we can still do that. And the one thing we did was when we found an integer feasible solution, we solved the nonlinear problem at that node because we wanted to find out if that was really integer. And that allows us to update the upper bound. So that's sort of an interesting alternative strategy. And it worked really well. So I don't have time here, but you can search the tree much, much faster with this strategy, especially if you have access to your quadratic programming solver. It allows you to do hot starts. So when you're racing down this tree, you're just changing one bound. And this one bound change corresponds to just setting one dual variable to 0 and then trying to shift it up from 0 as you're shifting this constraint to being feasible. And that can be done very efficiently by reusing the factorization, similar to the dual simplex method for linear optimization. Okay, so nonlinear branch and bound. I went sort of through this a little bit. There's a lot more that you need to take care of. I didn't talk about the software infrastructure, so it's really important to build on other frameworks. And there's a dirty little secret behind Minotaur, the code that Ashutosh wrote when he was at Argonne, which is that the class structure that we designed was actually stolen from Quen, which is Pietro's code. So if there's open source software out there, people will use it, and especially if it's good open source software. And it's good to exploit linearity or quadratic optimization problems as much as possible. So you can either do this for computing these estimates early on, that helps, or by actually searching the tree, the branch and bound tree. But this requires that you actually have access to the insights of your nonlinear optimization solver, and that is sometimes harder to do. And it works for certain classes of solvers and not so well for others. That's all I wanted to say about nonlinear branch and bound. So you're now up to date with that, and we'll have about 5 or 10 minutes, and then we'll start a tutorial. So, but please ask me questions if anything or everything was unclear.
Sir?
Yeah?
Sir, in the node selection, you were saying that heap should be as small as possible.
No. Not necessarily, no. I was saying that for the depth first, the size of the heap is minimized. But
Size is number of is how much we should store in that
yeah,
thing.
yeah.
So basically the size of the heap should be depends on
The search strategy. It depends on the search strategy. So there's one strategy which you can choose the smallest heap, and then there's other strategies which have a larger heap. But there's usually a lot of space on the heap, so you can certainly have millions of nodes on there. I think that's not an issue. And some solvers then also write them to disk potentially if you needed to, but you probably don't want to do that. I think the strategy is not to minimize the heap, but to solve the problem as fast as possible. And, oh yes, ideally what you want is you want a branching strategy that gives you the smallest tree. But nobody knows what that branching strategy is. So here's an interesting question. Can you teach an AI how to do branching and node selection smarter? Can an AI learn how to do that? And I see some of you already laughing. You might be. Have you played with that, Mustafa?
No, we had discussed that sometime in the lab.
Yeah.
Among us.
Yeah. Yeah, go on.
So in the depth first search, you mentioned the disadvantage method. The disadvantage of depth first search, I want to know why what's this?
Oh, the advantage of depth first is that it minimizes the size. Well, there's two advantages. It's easy to implement. Oh, the disadvantage. It's not very good if you can't find an upper bound. So if you keep going down the tree and running into nodes that are infeasible, then you're not gaining any information that helps you decide that you can prune other nodes. And you sometimes then explore nodes with a lower bound that are larger than the actual solution eventually is. So that's sort of not a good strategy in that case. And it can really run a long time. So you can I think with some of the branch and bound solvers, certainly with mine, you can play with these strategies and you can see that they're not very good. Some of these early simple strategies. You can set the node selection strategy. You can select the branching strategy. On all the solvers, you can select those. And you should play around with those. So in AMPL, that's when you write options, for example, K-nitro, options, and then you say something about the node selection strategy. So you can play around with different strategies and see how bad you can do compared to how well they're doing if they're well tuned, or how much better you can do compared to what they're doing. Yeah. This one, yeah. So the reason is, yeah, exactly. Because we have a linear set of constraints. The relaxation for convex problems, we found it's infeasible. We'll leave it alone. We don't need to go any further. Yeah. Yeah, you just drop it, yeah. And there's a similar trick for the objective function. So what you do with the objective, actually, I don't know if I want to keep you longer because you have to have a break. So typically the objective of a quadratic optimization problem is f at the point around which you linearize the gradient of f and then plus a Hessian term. And the problem is that quadratic functions neither under nor overestimate nonlinear functions. So you can find a nonlinear function for which the quadratic is an overestimator and also an underestimator. So you know this is not a lower bound. But you know that this guy here, this is a lower bound. So what we do is we take the trick, we define eta to be greater or equal to that, and then we have another constraint that says eta less than or equal to the upper bound. And now we use the eta trick to get us, or the upper bound minus some epsilon. Now we can use this trick to throw the linear part of the objective as a constraint, and then we can have the same, then it fathoms when it's infeasible. So that's sort of done automatically as well. And it's again because the linear function, a linearization of a convex function is an underestimator, and this quadratic term doesn't actually matter.